Hello, I welcome you all. The problem reads if the 20 kg cylinder is released from rest at h equal to 0, determine the required stiffness K of each spring so that its motion is arrested or stops when h is equal to 0.5 meters. Each spring has an stretched length of 1 meter. Right, so let's call this point 1. We call this point, so we say 1, this one 2. Alright, so we've been told the unstretched length of the spring is equal to 1 meter. Let's call length 1 of the spring length 8. This one is just going to be equal to 2 meters at h equal to 0. L2 is just going to be equal to 2 squared plus 0.5 squared square root. Therefore L2 will just be equal to 2 squared plus 0.5 squared. What is square root of that? So we'll just leave it like this. Okay, that is at h equal to 0.5. Okay, so using the conservation of energy, we say the kinetic energy at point 1 plus the potential energy at point 1 is just equal to the kinetic energy at point 2 plus the potential energy at point 2. Alright, of course this represents the kinetic energy and this represents the potential energy and gravitational and elastic potential energy. So T1, this is released from rest, therefore this is equal to 0. V1G, if this is our datum, we are going to choose this as our datum. Okay, so this is 0. And then V1E, which is elastic potential energy at that point, is just equal to half K L1 minus L0 squared. Then we have T2, kinetic potential energy. We are going to have a value, we'll call it this. And then T2G, we are going to have also, it will just be minus times H. Okay, then this is not T, it is V2G. Then V2E is just equal to, and here the springs are 2, so we have to multiply this by 2. So I'll say this is by 2, like so. Okay, even here it will be by 2. Then half K L2 minus L0 squared, like so. Okay, so let's put that replace that in an equation. So what do we have? We do have a 2 by half K. A K here is what we are looking for. Okay, and then L1 is just a 2 minus L0, which is just a 1, right? But okay, 2 minus 1 squared then equals to half the mass is 20 Then V2, that's what we are looking now. V2, V2, this part, V2, so I need to mention, I'll mention this later on squared. Okay, I'll mention this is equal to 0. Okay, I'll mention this. Well, let me just mention it in advance here. This part, this is equal to 0, so this is just equal to 0 because motion is arrested, okay, at h equal to 0.5. all right, this is vital, so this will just be a 0 here. Okay, then we have minus w, which is just a 20 by 9.81 by h, which is just a 0.5, and then we do have plus, we have a plus. Let me move this, I move it somewhere like so. We have plus plus this, where is it? So we have this, then plus 2 by half again, okay, L2, which is just square root of 4.25 minus 1 squared. Okay, so this is about it. So now, making K subject to the formula, what do we have? Curve, so we need to move one the other side. Alright, so it's just 20 by 9.81 by 0.5, right, and then we'll say divided by, it has gone the other side, divided by square root of 4.25 minus 1 close. Okay, we have closed this and squared. Okay, minus just minus 1, right? And we close. Right, so K here is a 773.08 newtons per meter. Let me check it once more again. Newton per meter. Let me check it. So square root of 4.25, okay, minus 1 squared minus 1, okay, and we do have that just 20 by 9.81 by 0.5 divided by answer 773.08. right, I think this is about it. We have found, of course, we do have a weight here. There's some weight there. It's just W. I think this is about it. We have found the spring stiffness, which is equal to 773.08 newtons per meter. I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screen.